This is part 2 of the AQA GCSE Chemistry 2022 Higher Tier Paper 1. Question 5. This question is about groups in the periodic table. The elements in group 1 become more reactive going down the group. Rubidium is below potassium in group 1. Rubidium and potassium are added to water. Predict one observation you would see that shows rubidium is more reactive than potassium. So it's great that they've given us this information here because it makes the answer easier for us. So we must be looking at the word more in our answer because we need to show comparison. So whatever we say, there has to be comparative language used. So what we've got to think about then is going down the group, everything is bigger or more. So we've got to think if potassium is added to water, what will happen? Some of the things that you may see are some flames. You might see some bubbling. You might see some movement around of your metal. So all of those things we should be thinking is bigger or is going to happen more. So we can easily say for 1 mark, there'd be a bigger flame. If we needed to write something else, in case it was 2 marks and 2 points we needed, we could say it catches fire more quickly. Or moves around more quickly. So that means anything above potassium, anything below rubidium, all of that would be different. Question 5.2. Explain why rubidium is more reactive than potassium. Right. So we remember that rubidium, as they've told us, is below potassium. So what does that mean in terms of difference in structure? If we were to draw a simple electron shell arrangement of potassium, it would look something like this. But for rubidium, it would look something like this. So what does that indicate to us? It indicates that there are more electrons. Definitely. So how is that going to be linked to reactive? Well, remind ourselves that metals always form positive ions. So that means that their tendency is to lose electrons. So if they want to lose electrons, that is what is going to contribute to them being reactive. Could be forming an ionic bond with a nonmetal, for example. But we have to remember that in the center of our atom, which is the nucleus, there is a positive charge. Our electrons, which are found in the shells, are negatively charged. So there is supposed to be some attraction because of this opposite charge of the electrons in the outer shell to the positively charged nucleus. But in a bigger atom, that attraction is going to be weaker because the distance from the outer shell to the nucleus is longer or greater in a bigger atom compared to a smaller one. So if we mention that, we are definitely going to be in a situation to get some marks. So first thing that we can definitely say here to pick up 1 mark is the outer shell of rubidium is further away from the nucleus. Remember that we have to use our comparative language because they have in the question used the word more. Next thing that we can say then is what does that now mean? That means that the attraction is less to the nucleus of the outer shell electron. So this means now that it's going to be easier for that outer shell electron to lose its place. From the atom. Question 5.3. Complete the equation for the reaction of rubidium with water. You should balance the equation. Okay, so what we first have got to remind ourselves then is we've got a metal, so it's a general formula here now. Metal plus water, what do we get? Well, if we react metal with water, we're always going to get two things. We're going to get a metal hydroxide and we're going to get hydrogen. So in this case then, we can easily put our first product, which will be hydrogen, so we know that's going to be H2. It's a diatomic molecule always. And then our rubidium and hydroxide. Now, remember that rubidium is in group 1, so it will want to form a positive ion, so +1 charge. But the hydroxide ion, OH, which we can put here now, that has a negative charge, and it's -1. So we know now that that should be our formula for rubidium hydroxide. We don't need to put anything else in terms of brackets because it's just cancelled out now in terms of charges. It's about balancing now. That's our next step. So when we balance equations, we need to count the amount of atoms for each element on both sides. So let's just write Rb, O, and H on our reactant side, Rb, O, and H on our product side. And let's count right now how many atoms of each do we have. Rubidium, 1. Oxygen is also 1. But there's a small 2 in front of hydrogen, so that means there are 2 atoms of hydrogen. Product side, rubidium is 1. Oxygen is 1. We have 2 hydrogens here, plus 1 in our rubidium hydroxide, so that gives us 3. So the only issue right now is the number of hydrogens. We need to get more on our reactant side than our product side. So our rules are we can only put numbers in front of our substances, and the smallest number that we can put is a 2. So let's try and do that. Let's put a 2 in front of our water, and let's see how that changes things. So that changes our hydrogen now to a 4, but that also changes our oxygen to a 2. We have 2 lots of oxygen, 4 lots of hydrogen. Okay, we can only change the oxygens and our products by adding a number in front of our compound rubidium hydroxide. So let's do that. So now, how many hydrogen atoms do we have? Well, we still have our 2 from hydrogen, but now we've got 2 from rubidium hydroxide. So that means the number of hydrogen we have on both sides is balanced 4. Let's check our oxygens. We now have 2 of them. So that is balanced in terms of oxygens on both sides. It's just checking our rubidium finally. So again, putting that big 2 means everything in front of it or behind it is multiplied by 2. So that means now that the number of rubidium atoms we have is 2. Okay, so our final step then is to try and balance the number of rubidium atoms. All we can do is just put 2 in front of that, and we are happy and balanced now. The noble gases are in group 0. Question 5.4. Which is a correct statement about the noble gases? Tick one box. Let's read through our options. The noble gases all have atoms with 8 electrons in their outer shell. Well, a few of them do. but not all of them. So that is not going to be fully correct. So that cannot be a correct statement there. The noble gases have boiling points that increase going down the group. At the top of our group 0, we have low boiling points, and then as you go further down, those boiling points do increase. So that is definitely a correct statement. Let's just check the rest. The noble gases have molecules with 2 atoms. Well, if we take krypton, for example, you don't have Kr2. So that's not true. And the noble gases react with metals to form ionic compounds. We know one of the properties of group 0 is that they're unreactive, also known as inert. So that's also not true. So you can definitely tick our second box now. Question 5.5. Table 1 shows information about 3 types of neon. The mass numbers are given to us, and so are the percentage abundances. Calculate the relative atomic mass of neon. Give your answer to 3 significant figures, 3 marks. So there's a general formula to find out the relative atomic mass of any element, and that formula is mass number multiplied by percentage abundance, and that's of the first isotope, because we're looking at isotopes here, plus mass number times abundance of isotope 2, and then if there is a third one, which in this case there is, we can add that. And then all of that needs to be divided by 100, because we are looking at percentage, so that means the total should be equal to 100. So if we were to add all of these 3 percentage abundances, it should equal 100%. So let's just plug in our numbers now, and then we'll see what our answer is. So let's do 20 multiplied by 90.48 plus 21 multiplied by 0.27 plus 22 multiplied by 9.25, and then all of that will be divided by 100. Plugging that all into the calculator, we should come out with a value of 20.2, which will be to 3 significant figures. There is a little trick that you can do when thinking about these types of questions. When you see the element name, in this case neon, you should go to the periodic table and then look at the mass number of that element. That mass number you can compare to your calculated value, because it should be the same if you round your calculated value. So in this case, if we were to round our calculated value of 20.2, we know that's going to be 20. In our periodic table, our mass number of neon is 20. So that's a little trick that you can do to check if you're on the right lines. Question 6. This question is about electrolysis. Molten sodium chloride is electrolyzed in an industrial process to produce sodium. Figure 8 shows a simplified version of the electrolysis cell used. So chlorine gas giving out, molten sodium also given out, and we've got 2 containers, both with molten sodium chloride. There was a mesh separating them too. We have a positive and negative electrodes as in normal electrolysis. So let's continue reading our question. 6.1. Which is the correct half equation for the production of sodium? Tick one box. Well, sodium, just like before, group 1 metal, wants to form positive ion. It has one electron in its outer shell, so that means it wants to just lose one electron. So we need to show a half equation that is showing that sodium is going to be formed from a sodium ion, which has a +1 charge. Cannot be the first one because we're looking at the production of sodium, not the production of sodium ions. So it cannot be that one. This next one cannot be correct because again it's showing production of sodium ion. That's not what we want. Having a look at this one here, we have a sodium ion plus an electron giving us our sodium metal. So this should be the correct answer here. Question 6.2. A mesh is used to keep the products of the electrolysis apart. Suggest one reason why the products of the electrolysis must be kept apart. So let's go back to our setup now. We have molten sodium chloride in both of these sections here. But we then have got one passage to produce and give out the molten sodium, and we've got one passage which gives out the chlorine gas. We need to think about why is there a separation here now. Well, let's think if there wasn't a separation, what would be the problem? Well, if there was no separation, you would start to form your molten sodium inside of this section here, and you would be forming your chlorine gas in this section here. If there was no mesh, what could just happen is the sodium and the chlorine could just react again together, and then you'd just be forming sodium chloride again. So then that would just defeat the whole purpose of the electrolysis, because your electrolysis is to split your ionic compound. So what we can say to ensure that we can get a mark now is to prevent products from reacting. In this case, it will be the sodium and the chlorine, just to say, to prevent remaking sodium chloride. 6.3. Which type of particle passes through the mesh in the electrolysis of molten sodium chloride? Tick one box. Well, as I just said, what's the purpose of electrolysis? Is you're trying to split up an ionic compound. In this case, sodium chloride, so we'd be splitting up the sodium and the chlorine, but really we will be forming the sodium ion and a chloride ion. So what would be able to pass through the mesh? Well, it won't be getting atoms. That's definitely not correct. Electrons, those are of course involved in electrolysis, because something is gaining electrons and something is losing electrons, but those won't be passing through the mesh. Those are going to be at the electrodes. Ions. So, as I just said, we've got sodium ion and chloride ion. In molten sodium chloride, the ion should be free to move. So, we would expect our ions to be able to move through the mesh as they are small. The reason why it cannot be molecule is because this chlorine molecule will be passing through at the top of the container and then leaving the setup, so will not pass through the mesh. Aqueous sodium chloride solution is electrolyzed in a different industrial process. Two gases and an alkaline solution are produced. Which two ions are present in aqueous sodium chloride solution in addition to sodium ions and chloride ions? Right, so aqueous sodium chloride. When we think of that word aqueous, we must be thinking of water, H2O. So we've got to think then that there's going to be two other ions. We obviously cannot say sodium ions and chloride ions now, that are also going to be present. Well, if you take that water and that water is able to be split up, you'll generate two ions from there. The first ion that you will produce will be H+, and the second ion which we will produce is hydroxide, which is OH-, as I mentioned in a previous question. 6.5. Name the alkaline solution produced. So we have got an alkaline solution, so that means something with a high pH. So we know now that it cannot be something that's just got hydrogen on its own, because that would be providing acidity. We then also can remember that hydroxide ions provide alkalinity. So it's got to be something that's containing hydroxide. So the only thing that can be produced with hydroxide, based on what we have read here, will be the sodium. So our alkaline solution that we should form is sodium hydroxide. 6.6. Explain how the alkaline solution is produced. You should refer to the processes at the electrodes. I'm going to draw the setup in a basic format as above. So we have our solution, which contains sodium chloride, which is our electrolyte, but this is an aqueous solution, so it has been added to water. We then have our electrodes, positive anode and negative cathode, and then that's connected to some sort of power supply. So inside of our electrolyte now, we should have Na+ ions, Cl- ions, chloride ions, then should have hydrogen ions, and I should have hydroxide ions. So we now need to think about how are we going to produce this alkaline solution, which we know now is going to be sodium hydroxide. So let's think about what's going on here now. So at our negative electrode, our cathode, it should be attracting positive ions. So the only positive ions in our solution are sodium and hydrogen. But we now need to think now which one of these two, because it can only be one of them, is going to be attracted to the cathode and then is going to gain electrons. Well, if we didn't identify that sodium hydroxide was the alkaline solution, then we could use the reactivity series to help us. Our reactivity series to help us, we can use this sort of mnemonic to help us. Please stop calling me a careless zebra. Instead, try learning how copper saves gold. So this allows us to identify certain elements that are more reactive than others. So if we find sodium, which will be here at the top of our reactivity series, it's quite reactive. The reactivity series allows us to also put in two nonmetals, our carbon and our hydrogen, because that allows us to identify also what will be produced during electrolysis and what can be reduced using carbon. So a hydrogen is below sodium in our reactivity series, so that means that hydrogen will be produced at the cathode. So that means at this cathode, we should get hydrogen gas. So that means the sodium ions will remain in the solution. The chloride ions, that's a simple negative ion. So that will always get formed at the positive electrode. So at our anode, we will form chlorine gas. So that means the hydroxide ions remain in solution. And then the sodium and the hydroxide ions will then, of course, form ionic bond and produce sodium hydroxide. So, as we have done, based on what the question has asked us, we should refer to the processes at the electrodes. So let's do that. So at the cathode, which remember is a negative electrode, hydrogen is produced. You can just make sure that we put hydrogen gas is produced. At the anode, we know that chlorine gas will be produced. What we can also do, just to make sure that we are specifying the processes, is that we can say what they are produced through, what processes. So again, it's to do with reduction and oxidation. So if our hydrogen ions are then going to form hydrogen gas, they have gained electrons to do that. So we can say by reduction. At the anode, we can say the chlorine gas is produced, got to be the opposite process, by oxidation. So if we know about our hydrogen and our chlorine, we can now then say the sodium ions and the hydroxide ions are left in the solution. And that should satisfy us 3 marks. Question 7. This question is about silicon and compounds of silicon. 7.1. The reactivity series, already mentioned, sometimes includes nonmetals such as carbon, hydrogen, and silicon, already mentioned. Silicon can be extracted by reducing silicon dioxide with different substances. The equation for one possible reaction is shown. Explain what this reaction shows about the position of silicon in the reactivity series. 2 marks. Wonderful that we've already recalled the reactivity series, so this will just make everything faster. So as I mentioned, we'll go back to the reactivity series here. It allows us to identify some non-metals. So our non-metal carbon is right here. So if an element is below another one in the reactivity series, that just means it's less reactive. So let's go back to the question. What's happening here? Carbon is reacting with the silicon dioxide, and then silicon is being produced on its own with carbon monoxide. So if the silicon is not with this oxygen anymore, and the carbon has bonded to it, that is clearly telling us that carbon is more reactive than silicon. So that would mean, in terms of the position in the reactivity series, that silicon is below carbon in the reactivity series. So let's formulate our answer here. Silicon is below carbon in the reactivity series. Now, what does this actually mean? In terms of the reaction now, what is the carbon actually doing? The carbon is displacing silicon. 7.2. Aluminium also reduces silicon dioxide. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper than aluminium. Carbon can be obtained by heating coal. Aluminium is obtained from aluminium oxide. Explain why aluminium is more expensive than carbon. 2 marks. So again, our reactivity series can help us. It's told us specifically about carbon, how that can be obtained. It's told us about aluminium, how that can be obtained. So let's go back to the activity series. As I said, the activity series also can help us to identify how certain metals can be obtained. So, are elements metals that are above carbon? These typically can be obtained through electrolysis. The elements or metals that are just below carbon, these typically can be obtained through reduction using carbon. And that would actually be in a blast furnace, for example. The elements that are below hydrogen, these are pure, so found in the earth. So not in any ore, for example. So let's look at what the two elements in the question they were asking us to talk about. Aluminium and carbon. So here they are. Aluminium is above carbon. So that already identifies to us that aluminium can be obtained, extracted through the process of electrolysis. So the problem with electrolysis is, as it said, it's expensive, but why is it expensive? For you to extract something using electrolysis, it requires a lot of energy. So that is going to mean that more money is needed for the process. So let's write that and then get our 2 marks. So first mark, aluminium can be extracted using electrolysis. This means that more energy is required. Magnesium also reduces silicon dioxide. The equation for the reaction is shown. 7.3. Give one reason why the products are difficult to separate if magnesium is used to reduce silicon dioxide. So let's look at the equation again. We've got magnesium, solid, silicon dioxide, solid, silicon solid, magnesium oxide solid. There are different separation techniques that we know: filtration, distillation, chromatography, fractional distillation. What will be the problem with using any of those separation techniques with what's going on here? Well, the thing is, all of these substances are in the same state, which is solid. So it's going to be very difficult for you to separate a solid from another solid. So that should be our answer here. All products are in the same state, solid. 7.4. Calculate the minimum mass in grams of magnesium to completely reduce 1.2 kilograms of silicon dioxide. The relative atomic masses of oxygen, magnesium, and silicon are given to us. 5 marks. So we are thinking about reacting masses here now. There are multiple methods that you can use to try and work this out. I'm just going to show the method that I commonly use. So I'm going to remind myself of the equation first. I'm just going to put that below. And then I'm going to write down the things that I need to find and I'm also given. So first thing that I'm given is a mass of silicon dioxide. I'm also given the relative atomic masses. And with those pieces of information, I'm able to find out the number of moles of certain substances. After that, I want to find out the molar ratio. And then if I am able to go there, I'm able to then work out the mass to finally get my answer. So in the question, I'm given a mass of silicon dioxide, which is 1.2 kilograms. But looking at my answer, it's in grams. So that tells me straight away I need to convert the silicon dioxide mass into grams. So 1.2 multiplied by 1,000 will give me 1,200 grams of silicon dioxide. I'm not given the mass of magnesium because I need to work that out, so that will be my question mark. And I don't have the masses of silicon or magnesium oxide either. I then am given the relative atomic masses of magnesium, so that's 24. I'm given it of silicon, 28. And I can easily work it out for magnesium oxide. So that'll be 24 plus 60, so that'll be 40. What I need to find now is the relative atomic mass of silicon dioxide. So that will be 28 plus 16 times 2, so 28 plus 32, so that will be 60. Okay, I'm now able to find the moles of the substance which I have the mass and the RAM for, because to find number of moles, that is equal to mass over molar mass, and mass is over RAM. So that will be for silicon dioxide, because I've got the mass 1,200, the RAM which is 60, so 1,200 divided by 60 should give us 20. The next thing that I need to find is the molar ratio. Why is that information beneficial to us? Because it will allow us to then find the moles of any other substances, so you can eventually find out the mass of the magnesium, which is what we want. So for us to find the molar ratio, we need to look at the equation again, and especially any numbers that are in front of it, because that tells us the moles of our substances. So just checking with our equation at the top, there is a 2 in front of magnesium, and there is a 2 in front of magnesium oxide. So what does that tell us our ratio is? That tells us our molar ratio is 2 to 1 to 1 to 2. So, as I've said now, that means if I've got 20 moles of silicon dioxide, the ratio of 1 to 2, that will mean that I will have double my moles of magnesium. So that means I'll do 20 times 2, and that should mean I've got 40 moles of magnesium. What I'm able to do now is look at my equation again, and I have 2 of the 3 things needed. I've got the RAM, and I now have the moles. So I can just rearrange the equation to find the mass. So mass will be equal to moles times RAM. If I plug in the numbers now, my number of moles is 40, my number for RAM is 24. I just multiply those together and I will come out with a final value of 960 grams. Si2H6 is a covalent compound of silicon and hydrogen. Complete figure 9 to show the outer electrons in a molecule of Si2H6. So covalent compound. If it's covalent, that means that there is sharing of electrons. And the figure has helped us to identify that that's the case because we've got overlapping circles. So we just need to remind ourselves about how many electrons in the outer shell of these two atoms here. Silicon and hydrogen. Hydrogen we know is going to have 1 electron, but silicon is in group 4, so that means it will have 4 electrons. So what we can then do first is we can see that this hydrogen is going to share a pair of electrons because it will need 2 to have a full outer shell with silicon. So that means if we use a dot to represent hydrogen and a cross to represent silicon, we can then put a dot in each of these overlapping circles for these hydrogen atoms here. Now what we need to do is just use our crosses to do that for silicon. Perfect. The only thing left now is if we notice the number of crosses for silicon, for each silicon atom, there are 3 and 3. So each one is missing 1. So the place to put them will be in the middle. And we have completed our structure. Question 7.6. Si2H6 reacts with oxygen. The equation for the reaction is shown. 30 centimeter cubed of Si2H6 is reacted with 150 centimeter cubed, an excess of oxygen. Calculate the total volume of gases present after the reaction. All volumes of gases are measured at the same temperature and pressure. 4 marks. So we are given an equation, which means we probably need to use it somehow. We're given values of volume, 30 for Si2H6 and 150 for oxygen. So we need to use that also. And it's total volume of gases. So at some point we'll probably need to do some addition. And then it says at the same temperature and pressure. So we've got to think, what does that mean? Well, at a standard and same temperature and pressure, we've got to use our volume constant, which is 24. So where do we start with this now? Well, we are given the reaction equation with 2 moles of Si2H6 and 7 moles of oxygen. We've got to now think, okay, if 30 centimeter cubed is going to react with 150 centimeter cubed of oxygen, which is an excess of that, we've got to think what volume of oxygen will actually react with this 30 centimeter cubed of Si2H6. So what we can do is figure out and use our number of moles here to do some calculations. So how many times does that 2 moles of Si2H6 go into our 7 moles of oxygen? Well, that would just be 7 divided by 2. So that will be 3.5 moles. We now know how much of the actual oxygen is going to react to this Si2H6. So 30 multiplied by 3.5 will be 105 centimeter cubed. So that's the actual volume that will react. So whatever is then left from this is going to be present at the end of our reaction. So let's just check. We actually added 150 centimeter cubed. So that was our total added. We need to subtract that from what actually reacts. So that's 105. So we're then left with 45 centimeter cubed. And this is of oxygen. So that already we know has been left. We know that the silicon dioxide is a solid. So we know that that's not something that we need to worry about calculating. Here's our water. So water vapor as a gas. We need to somehow now find a volume for that, and then we'll be almost complete. So what we can then do is figure out how much of our moles of silicon compound will react to get 6 moles of water. So just like we did before, 6 divided by 2 is equal to 3. So that will be 3 multiplied by our 30, and that will give us 90 centimeter cubed. So that will mean that we'll have 90 centimeter cubed of this water that we will be producing. So what's left to do then is to find the total volume, which is adding them up. So that'll be 45 plus 90, which will give us 135 centimeter cubed. The other way in which we could calculate this and still get to a value of 135 is by using our equation for moles or volume of gases. And that would require us to use this value of 24 using this equation also, which is volume equals moles multiplied by 24. Question 8. This question is about acids and alkalis. Explain why the pH of an acid depends on the strength of the acid and the concentration of the acid. 4 marks. So, when thinking about pH, we have to remember what that's got to do with. So pH means power of hydrogen. And when thinking about concentration of the acid, which we can start with first, that makes sense. Because if an acid has a low pH, so let's say for example a pH of 2, that means that the acid has got a high concentration of hydrogen ions. If an acid has a higher pH, for example pH of 6, that means it has a lower concentration of hydrogen ions compared to this acid with a pH of 2. So what we can say first is our fundamentals of how pH works. An acid with a low pH has a higher concentration of hydrogen ions. So if we increase the concentration of our acid, we should technically then have a even higher concentration of H plus ions, and that means that the pH will be even lower. But what about the strength of the acid? Well, strong and weak acids, how are they different? let's just recall it, and it should make some point for us to get a mark. A stronger acid completely or fully ionizes in aqueous solution. So a weaker acid partially ionizes. So what we've done now is we definitely made this basic link between pH and hydrogen ions. And now what we have done also is we've mentioned the ionizing ability of strong acids and then compared that to weak acids. And also what happens if we increase the concentration of the acid, how that affects the pH. So we've definitely got our 4 points here. 8.2. A student titrated 25 centimeter cubed of hydrochloric acid with a 0.1 moles per decimeter cubed barium hydroxide solution. Table 2 shows the results. So we have 5 titration numbers and the volume of barium hydroxide solution used in each case. The student calculated the volume of barium hydroxide solution to be used in the titration calculation as 23.5 centimeter cubed. Explain why the student used a volume of 23.5 centimeter cubed of barium hydroxide solution in the titration calculation. 2 marks. So let's look at our values now and do some analysis. First titration number is 23.9. Now in titration, you can see that the precision of the values is quite high. So what we can do is we can compare this 23.9 to 23.5. And in the case of it, it is a fair distance away. Let's compare the rest though, just to check. Second titration number, we get 23.45, so that's quite close. Third is 23.55, so that's quite close. Fourth is the same. And fifth is the same as 2. So what we've already done now is we've identified now that 23.9 is quite far away. We can say that that's the odd one out, but in science, what word do we actually use? We use the word anomalous. So value of 23.9 is the anomalous value. So what do we normally do with anomalous values? We exclude it from the mean. So what values did they use in their mean? It's titration numbers 2 to 5. And if you were to find the mean of 2, 3, 4, 5, if you actually calculated it, you probably will come up with a value of 23.5. So that would make sense. 8.3. 25 centimeter cubed of the hydrochloric acid reacted with 23.5 centimeter cubed of the 0.1 moles per decimeter cubed barium hydroxide solution. The equation for the reaction is shown. Calculate the concentration of the hydrochloric acid in moles per decimeter cubed. 4 marks. So what this question is going to require us to do is we're going to have to use the values and then try and work out the number of moles here. But we also need to refer to the equation at some point because it's going to help us to do the calculation properly. So we can use this little formula to help us work it out because the purpose of this titration is with neutralization. Remember, we've got an acid and we've got a base and we're going to form a salt and water. So we can use this little formula here. C1 V1 equals C2 V2. The C1 stands for concentration of first substance, V1 stands for volume of first substance, C2 is concentration of second, and volume of second. So in this case, we can take our C1 to be hydrochloric acid, and our C2 to be our barium hydroxide. So what are we trying to work out? We're trying to work out the concentration of the hydrochloric acid. So that will be C1. But if we multiply this by our volume, we will get the number of moles. Okay, so in this equation, moles, which is N, is equal to CV. So our volume that's given to us in the question is 25 centimeter cubed. However, if you look at our units for concentration, it's in decimeter cubed. So we need to convert this centimeter cubed to decimeter cubed. So to do that, we need to divide by 1000. So 25 centimeter cubed will actually be equal to 0.025 decimeter cubed. So we can plug that into our equation here. And then that will be equal to our concentration of barium hydroxide, which was given to us as 0.100. And then we need to multiply that by our volume. Again, we need to convert. So 23.5 divided by 1000, that will give us a value of 0.0235. So what we're able to do now is we're able to simplify this. If we calculate 0.1 multiplied by 0.0235, we'll come out with a value of 0.00235. And then that will be equal to 0.025 multiplied by C1. But at this point, we need to stop because we have to go to our equation because we're about to find out the concentration of this hydrochloric acid. However, whatever moles that we find out now, we have to compare that to our equation. And just like before, we're looking at the ratio. So looking at the numbers in front of our reactants here, there's no number. So for barium hydroxide, the ratio is 1. But for hydrochloric acid, the ratio is 2. So that means for every 1 mole of barium hydroxide, we actually have 2 lots of hydrochloric acid. So what that would require us to do then is to multiply this value that we've just calculated by 2. So to find 0.00235 multiplied by 2, we would come out with a value of 0.0047. And that would be the moles of hydrochloric acid. So we would actually need to take this value and then put that in our equation to solve for C1. So it would be, to find our concentration, it's going to be our moles, which is 0.0047, divided by our volume, which you know is 0.025. And that will give us a concentration of 0.188. And that will be our final answer. Another student titrated sulfuric acid with barium hydroxide solution. The equation for the reaction is shown. The student measured the electrical conductivity of the mixture during the titration. The better a conductor, the higher the electrical conductivity value. Figure 10 shows the results. So we've got a graph here, volume of barium hydroxide solution added on our x-axis, and electrical conductivity in arbitrary units on our y-axis. So we can see as the volume of barium hydroxide increases, the electrical conductivity is actually decreasing. 8.4. Explain why the electrical conductivity of the mixture was 0 when the sulfuric acid had just been neutralized. Use the equation for the reaction. Refer to ions in your answer. 3 marks. So let's go back to the equation. Again, as they have mentioned in the question, it is to do with neutralization. So our acid is being neutralized by the base to give us this salt and water. So if we're forming this salt, it is going to contain ions. It's going to be an ionic compound. So the barium is going to provide the positive charge and the sulfate is going to provide the negative charge. But in this aqueous solution, we should have ions that are free to move. And that would explain how you have the conductivity. So, why is it going to be 0 when the sulfuric acid had been neutralized by barium hydroxide? Well, you can simply say that the ions are not free to move. And really, it's a similar thing to electrolysis and also our question referring to metallic bonding. Because to get a conductivity, that must mean there is a charge. Charge can be provided by ions moving or by electrons moving. So the fact that the ions are not free to move means that they can't carry the charge. If we think about this barium sulfate, as we identified from the equation, the barium sulfate is a solid, so definitely won't be moving, and it's insoluble, so it also won't be able to be dissolved, form ions, and then those ions are free to move. But going back to the equation one more time, we also have water, because remember it was an aqueous solution, so potentially there could be hydrogen ions or hydroxide ions that could have been able to carry a charge. But what we can see is those ions have formed water. So the hydrogen ions and the hydroxide ions have gone to form water. 8.5. The student then added a further 10 centimeter cubed of barium hydroxide solution. The electrical conductivity of the mixture increased. Give one reason why. So we had formed barium sulfate, which we said was insoluble. We have then added some more barium hydroxide, which again was an aqueous solution. So what is being provided now from this solution are Ba ions, it's actually 2 plus because it's in group 2, and hydroxide ions. So then if these are being provided in an aqueous solution, these are going to be free to move and then allow the charge to be carried. So we can say that the barium and hydroxide ions can be free to move and carry the charge.